Free body diagram questions about objects being pulled at awkward angles. We'll start out with our force of gravity first. Okay. Next comes that awkward pull force. We'll have it go like this. We'll call it F pull net is what I want to name it. F pull net is equal to 115 newtons. Now that force is broken down into two residual forces. We have our horizontal component of force, and we have our vertical component of force. Since that angle is 30 degrees, we should be able to do trig effectively to solve for those two forces. Now this is the adjacent side of the triangle for the horizontal component of pull force. So you would set up, if we don't really set up trig functions too often, let's do it real quick. F of x over net pull force is equal to cosine of 30. Sine of 30 is equal to f of y, vertical component of pull force, over 1/15, that net pull force. Landing on those two numbers, we get a f of x of 99.6. We get a f of y of 57.5. And now we're kind of done with the net pull force. I don't want to say scratch it out and forget it. What I will say for our purposes when we're summing up the forces, you've kind of already accounted for that. Now you want to leave that vector there if we're grading on the basis of a complete free body diagram, but we can kind of ignore that number 115 now that we've broken it down into its appropriate x and y components. For example, when we want to solve for our normal force, our initial inclination is to set that normal force equal to 300. It's not, because we're compensating for that y component of vertical force, such that our net forces in the vertical direction and the vertical components of motion, our net forces are approximately equal to 0, since this sled contains no vertical motion, which means our net force in the vertical direction is 0. 0 is equal to force of gravity minus that y component of pull force minus that normal force. Plugging in arithmetically, now to be clear, this is an equation that we memorize. This is an arithmetic expression that's problem specific to each situation. My normal force, when I sum that up, I land on normal force 242.5 newtons. That takes care of my vertical components of force. As far as horizontal components of force goes, I know I've got only one component of horizontal force other than that f of x equaling 99.6, and that's my force of friction. You might be wondering how to solve for that. It's really not too terribly difficult. We say in the problem that the girl is pulling this object with a constant velocity. Force of friction is therefore equal to horizontal pull force. And if you notice, all of our forces balance out to equal a net force of 0. All of our forces in the vertical direction balance out. We have a net force in the vertical direction of 0. We have no vertical motion. We're not speeding up or slowing down at all in the vertical direction. Summing up our forces horizontally, also canceling out. The net force acting on this object is equal to 0. Now I know that's a little counterintuitive. Wait, the net force is equal to 0, yet it's still experiencing motion. It is, but it is not speeding up nor slowing down, in keeping with Newton's first law of motion. Finally, what's the coefficient of kinetic friction for the system? We would use the equation force of friction is equal to our normal force times coefficient of kinetic friction equation. Plugging it appropriately in this situation, coefficient of kinetic friction in this situation is equal to 0.41. Remember, coefficients of friction contain no units, so 0.41 is appropriate and a correct answer.